Now that we've looked a little bit informally about distance, and especially in Euclidean geometry, let's return a little bit to a more formal analytic approach to distance and order. So all the earlier material in this section is an informal approach. We talked about distance, order, dimension. Now let's turn our attention to a formal approach to distance and order. We're going to carefully develop rigorous concepts of a metric system, between, a coordinate system, definitions of line segments and rays over the next few videos. But for now, let's examine the later definition of a circle and some related geometric figures. So here's some formal definition. A circle is a set of points in a plane which are a fixed distance, called the radius, from a given point called the center. A line segment with one endpoint at the center of a circle and the other on the circle is called a radial segment. A line segment with both endpoints on a circle is called a chord of the circle. A chord containing the center of the circle is called a diametric chord. The length of a diametric chord is called the diameter of the circle. Of course, that will be twice the radius. The length of a path starting on a circle and following around the circle back to the original point is called the circumference of the circle. The set of points whose distance from the center of a circle is less than the radius form the interior of the circle, and the set of points whose distance from the center of the circle is greater than the radius form the exterior of the circle. So I want to point out a couple of things right away. It's not uncommon, in fact, it's quite common for people to use the word radius for two different things. They use the radius for the um, distance from the center to the point on a circle, and they also use the radius for a line segment going from the center point to a point on the circle. I think that's a little problematic because we want to make a distinction between um, numbers and geometric figures, sets of points. So we're going to make the distinction there between a radius, which is a number, and a radial segment, which is a line segment, a set of points. Similarly, we're going to make a distinction between a diameter, which is often used for both the that word is often used for both a distance and a line segment. We're going to make that two different things. A diameter will be the distance, and the diametric chord will be the line segment. It has that length. Notice the circle is just the points on the circle, the ones that are actually the same distance from the center point. The circle is an example of what we're going to know as a closed plane figure. It's going to divide the plane up into three parts: the interior of the circle itself, and the exterior of the circle. So here's a task for you. In GeoGebra, create a general circle and create each of the geometric figures and measurements mentioned in these definitions. This is not a terribly difficult assignment given the tools that are built into GeoGebra, but it's a good one to get you started using the tools there. You should always memorize all the definitions that we'll be using in class, including these, and the definitions that we're going to do, like these, are designed carefully and worded very carefully so that they will work in all of the geometries we're going to be studying as part of unified geometry. Certainly they're appropriate for Euclidean geometry, but there'll be exactly the same definitions in the other geometries that we'll study. However, because the difference in the distance metrics and the interpretations of the various geometries, these may be different objects and different geometries. For example, a circle might look very different, say in Euclidean geometry versus taxicab geometry. In a formal analytic approach to geometry like that of G.D. Birkhoff, right up front, we assume that we know all about the real numbers and their properties, and then we have postulates that ensure the existence of measures for distances and angle measures. In particular, at the beginning, we establish a one-to-one correspondence between the points on any line and the set of real numbers in such a way that any line can be viewed as a coordinate system, in other words, a number line. Here are Birkhoff's definitions of postulates related to distance and order. And this week, a little bit later video, we will be adopting very similar statements to these in our formal treatment of unified geometry. So he has distance is an actual undefined term, and he says the distance between any 2 points A and B is a non-negative real number, d of AB, such that d of AB is equal to d of BA. In other words, the distance from A to B is the same as the distance from B to A. And then with that undefined term, then he can define what we mean by between. Remember, between was left as an undefined term in Hilbert's synthetic approach. So the definition of a between is if A, B, and C are distinct points, we say that B is between points A and C, A dash B dash C, if and only if distance from A to B plus the distance from B to C equals distance from A to C. We're going to have a very slight different definition of between because our version is going to require that the points be collinear as well. A line segment can be defined then. The points A and C are together with all the points B between A and C form the line segment AC. A half line, also known as a ray, and endpoint are defined. The half line M prime with endpoint O is defined by 2 points O and A in line M, where A is not O, as the set of points A prime of M such that O is not between A and A prime. And then he has a postulate of line measure. The points A, B, and so forth of any line can be put into a one-to-one correspondence with the real numbers x, so that the x of B minus x of A absolute value is the distance from A to B for all points A and B. And so we're going to have some very similar versions of postulates that we're going to formally introduce in a little bit. But before we return back to our formal exploration of unified geometry, we're going to introduce 4 infinite geometries. We're going to be introducing Euclidean geometry, which you're already familiar with, but also models for hyperbolic geometry, spherical geometry, and taxicab geometry. All 4 of these geometries satisfy 8 of the 9 existence and instance postulates for unified geometry that we've introduced so far. And we'll modify one of them, the remaining one, so that spherical geometry works as well. And then we'll have a set of postulates, definitions, and propositions that will work, at least up to a certain point. They will work in all 4 of these geometries. So we're going to call these the 4 basic infinite geometries, and they're all including in this more general unified geometry that we're going to be studying. So we'll be exploring and introducing these 4 geometries first, then we'll return back to our formal exploration and development of unified geometry.